Hi everyone, today I'm going to talk about the pressure-based and density-based solvers in CFD. Both the pressure-based and density-based solvers are used to solve the mass and momentum conservation equations which describe the fluid flows. Every fluid flow must satisfy the equations of continuity and momentum as shown here in the differential form. As can be seen, there are 4 equations and 5 unknowns, which are 3 components of velocity, a pressure, and rho density. The 5th equation is the equation of state. Therefore, density is obtained by the continuity, velocity by the momentum equations, and pressure by the equation of state. This set of equations is used for compressible flows at high speeds. In other words, for compressible flows, the continuity equation is a transport equation for density that, together with the internal energy equation, determines the pressure by the thermodynamic relationship of the ideal gases law. The density-based solvers are mainly used for compressible flows, which are encountered at high speeds. These solvers are also referred to as the coupled solvers. However, the pressure-based solvers are historically developed for low speed incompressible flows where the density is assumed to be a constant value. The pressure-based solvers are also referred to as the segregated solvers. Let's first talk about the pressure-based solvers. Pressure-based solvers. The pressure-based solvers are developed historically for low speed incompressible flows where the density is assumed to be a constant value. In these solvers, the mass and momentum equations, as shown here for incompressible flows, are solved in a segregated uncoupled way. In other words, the governing equations are solved in a sequential manner to find the variables, which are 3 velocity components and pressure. For simplicity, the continuity and momentum equations are shown here for one-dimensional incompressible flows. In the finite volume method, the governing equations are written in the form of a transport equation for a general scalar variable phi, as shown here. The first term is the transient term, which shows the rate of change of phi. The second term indicates the convective term, which shows the transport of phi by the fluid flow motion. And the third term is the diffusive or viscous term. Finally, we have the last term, which is the source term. Phi here can be any variable such as velocity, pressure, turbulence, or energy. So as we are considering the one-dimensional case, we will use this one-dimensional uniform grid over which the transport equation for the variable phi will be discretized. Here, uppercase W, P, and E indicate the centers of the western, central, and eastern control volumes respectively. The west side phase of the central control volume is referred to by the lowercase w, and the east side phase of the central control volume by the lowercase e. The distances between the nodes W and P and between the nodes P and E are identified by delta x W and delta x E respectively. Similarly, the distance between phase W and phase E is denoted by delta x. In the finite volume method, the transport equations will be integrated over each cell as shown here. Various discretization schemes have been proposed to convert these equations into algebraic equations. Therefore, by utilizing suitable discretization schemes, this integral equation can be approximated to an algebraic equation as shown here. Here, phi p is the value of phi in the cell P. Phi nb indicates the values of phi in the neighboring cells. As these algebraic equations are nonlinear in nature, iterative methods are used to obtain a solution. The reason for nonlinearity of these equations is that the coefficient a and b and ap are functions of phi as well. Therefore, the use of direct methods to solve these nonlinear equations is avoided, and instead de-derivative methods are used to handle these nonlinear equations. Now let's go back to the continuity and momentum equations for one-dimensional incompressible flows as shown here. Thus, for incompressible flows, while we have an equation for mass and momentum, there is no explicit equation for pressure. Therefore, the question that arises here is that how can we estimate the pressure when we have no explicit equation for pressure? This leads us to the development of pressure-based solvers, where an attempt has been made to link the velocity field to the pressure field. Here, first, the simple algorithm, which was proposed by Patinker 1972, is presented. SIMPLE stands for Semi-Implicit Method for Pressure-Linked Equation. This algorithm constitutes the most popular pressure-based solver in the CFD community to link the pressure and velocity fields. Simple algorithm. For the staggered grid arrangement over a one-dimensional uniform grid, as shown here, the discretized form of the momentum equations at the east face side can be written as shown here. B indicates any source term which can come from body force. For example, AE is the area of the east face side. Note that in the staggered grid, as opposed to the collocated grid, the velocity and pressure values are stored in different nodes, as we can see here. This is done to eliminate the so-called checkboard problem in the pressure and velocity fields. For more information about the staggered and collocated grid arrangements, you can watch the video in my channel entitled Simple Algorithm in Staggered and Collocated Grid Arrangements. You can access the video using the link given at the top right corner of this video. We start the solution by an initial guess for the pressure field, which is shown here by P asterisk, and then the momentum equations are solved to obtain the corresponding guessed velocity field, U asterisk. P asterisk here in this discretized equation is the guessed pressure or the pressure value at the previous iteration. Here we are going to try to improve the guessed pressure field in order to obtain a velocity field which satisfies the continuity equation. Therefore, we use the following equations to correct the pressure and velocity fields. P asterisk and U asterisk are the guessed or previous pressure and velocity fields, while P prime and U prime are the pressure and velocity corrections respectively. So we show the correction made in the velocity by means of the pressure correction as U prime. If we subtract the discretized form of the momentum equation from the discretized form of the momentum equation in which the guessed pressure and velocity fields are used, we obtain the following equation which relates the velocity and pressure corrections. This equation can be simplified by ignoring this phrase. Therefore, this relation here can now be written as follows, where dE is defined here. Note that dropping this phrase is reasonable since we are talking about the pressure correction equation, not a conservation equation. This last equation is known as the velocity correction equation. The pressure correction equation can be obtained by substituting the velocity correction equation into the discretized continuity equation as shown here. The last two terms are mass sources indicating the residue. Our goal here is to use the pressure correction to eliminate this residue. So a quick summary of the simple algorithm is presented here. The density is computed from the equation of state. The velocity and pressure fields are specified from initial or previous iteration. Also, the boundary conditions are imposed. Through solving the discretized form of the momentum equations, the intermediate velocity field U asterisk is obtained, and the mass fluxes are computed. the pressure correction equation is solved to provide the cell values of the pressure correction P prime. The pressure, velocity, mass fluxes, and density are corrected. Other transport equations such as turbulence and energy are solved. Steps 1 to 7 are repeated until the convergence is achieved. Therefore, the pressure-based solvers such as the simple algorithm are based on a pressure-velocity coupling algorithm where a pressure correction equation is employed to fulfill the mass conservation constraint on the velocity field. The pressure correction equation is obtained from the continuity equation and is used to correct the pressure in such a manner that the predicted velocity field fulfills the continuity equation. For this reason, the pressure-based solvers are also referred to as the predictor-corrector approach. Weakness of the simple algorithm. The main weakness in using the simple algorithm is the slow convergence of this method. The reason for this is the estimated nature of the pressure correction equation. As you may remember, to obtain this equation, the influence of the neighboring cells is neglected. As a result, the values of the corrected pressure obtained in this way become very large, and there is a need to reduce the rate of change of these values. That is why we use under relaxation factors to update the pressure and velocity values as shown here. Here, phi OP is the initial or previous value of the variable phi at P. Delta phi P is the variation of the variable phi at P in an iteration. Alpha is the under relaxation factor. As a consequence, this slows down the convergence rate. Therefore, another method of pressure calculation has to be found. Simpler algorithm. The simpler algorithm, which stands for the simple revised, is an improved version of the simple algorithm. In this algorithm, to improve the convergence speed of the simple algorithm, a somewhat different procedure is adopted. First, note that the discretized momentum equations at the east phase side can be rearranged as shown here. A pseudo-velocity is defined based on the guessed velocity field as shown here. Therefore, the velocity here can be written like this based on this pseudo-velocity. Substituting this new velocity equation based on the pseudo-velocity into the discretized continuity equation gives the following discretized equation for pressure. The pressure that is obtained from this equation is set as the guessed pressure field, and then the momentum equations are solved to obtain the corresponding guessed velocity field U asterisk. After that, the pressure correction equation as shown here is solved. Then, using the pressure correction values, the velocity is corrected using the velocity correction equation as shown here. Note that, contrary to the simple algorithm, the simpler algorithm does not correct the pressure at this stage, and the correction is only applied to the velocity field. So there are two main differences between the simple and simpler algorithm. First is the use of the pseudo-velocity to obtain the guessed pressure field from a discretized equation for pressure in the simpler algorithm. Okay, and the second one is that the pressure field is corrected differently. The simple algorithm corrects the pressure using this equation, while the simpler algorithm corrects the pressure indirectly through correcting only the velocity field. The simpler method has a better performance than the simple method because in the simpler method there is no need to guess the pressure field properly. The simpler method can obtain the pressure field through a properly guessed velocity field. And guessing the velocity field is much easier than guessing the pressure field. For example, the velocity field for the whole computational domain can be considered equal to the velocity field at the upstream inlet boundary. Simple C algorithm. This algorithm is similar to the simple algorithm except for the velocity correction equation. The simple C, which stands for simple consistent, seeks to reduce the effect of this phrase ignored in the simple algorithm. In the simple algorithm, we obtain the following equation, which relates the velocity and pressure corrections. Here, we subtract this phrase from both sides of this equation, and as a result, we will have this equation. Neglecting the first item on the right hand side, we are going to have the velocity correction equation as shown here, where dE is defined using this equation. So the difference between the simple and simple C algorithm is in the definition of dE, as we can see here. PISO, pressure implicit with splitting of operators. This algorithm, which was proposed by ESA 1986, is used for transient simulations where the use of small time step is necessary for temporal accuracy. Essentially, the PISO algorithm is a variation of the simple algorithm with additional characters to speed up the convergence. The first characters that are used within the PISO algorithm are very similar to the simple algorithm as shown here. Using the exact procedure as that used in simple, we get the following equations for velocity correction and pressure correction. Therefore, the first character in the PISO looks exactly the same as the simple. However, in PISO, there are several subsequent characters that we use to accelerate the convergence. Thus, based on the correction that we introduced, we are going to have an equation for momentum as shown here. The next step is doing an explicit update of the momentum equation using the older values of the calculated variables as shown here. On the left hand side, we have the UE triple star, while on the right hand side we have the velocities double star, and also we have the pressure values double star. Subtracting this equation from this one, we are going to have the following equation. This is an equation which gives us the updated velocities. In this case, we are not going to neglect the influence of the neighboring cells in updating the velocity values. Finally, by substituting the updated velocity values into the discretized continuity equation, we get this equation. This pressure correction equation looks identical to the pressure correction equation obtained for the simple algorithm. The last two terms are mass sources indicating the residue. Our goal here, again, is to use the pressure correction to eliminate this residue. Therefore, as we are using additional characters and also as we are including the effect of the velocity values of the neighboring cells in these additional corrections, the PISO algorithm offers a better performance in correcting pressure compared to the simple algorithm, and consequently it provides a better convergence rate than the simple algorithm. Summary of the PISO algorithm is presented here. Note that in the PISO algorithm we have two steps, predictor and corrector. First, the predictor step is presented here. Predictor step, the density is computed from the equation of state. The velocity and pressure fields are specified from initial or previous iteration. Also, the boundary conditions are imposed. Through solving the discretized form of the momentum equation, the intermediate velocity field is obtained. PISO coupled transport variables are solved. Total enthalpy and active scalars. The mass fluxes are computed. The pressure correction equation is solved. The pressure, velocity, and mass fluxes and density are corrected. PISO coupled transport equations are solved. Now the corrector step, the density is computed from the equation of state. The velocity and pressure fields together with boundary conditions are updated. Momentum is updated explicitly. The mass fluxes are computed. The pressure correction equation is solved. The pressure, velocity, mass fluxes, and density are corrected. PISO coupled transport equations are solved. And repeat the corrector process from 9 to 15. PISO uncoupled transport equations such as turbulence and energy are solved. The main difference between the predictor and corrector steps is instead of solving the momentum equations in the corrector step, we are just doing an explicit momentum update. Therefore, as can be inferred from this workflow, for the PISO algorithm, the calculations involved within each time step in the PISO algorithm are higher than the simple algorithm. Density-based solvers. The density-based solvers are mainly used for compressible flows which are encountered at high speeds. In these solution algorithms, which are based on what are known as Riemann solvers, explicit or implicit time marching procedures are employed to solve the governing equations. The density-based methods solve the governing equations for continuity, momentum, and energy simultaneously, i.e. in a coupled manner. The equations for turbulence quantities are solved in a segregated manner outside the coupled solver. The governing equations solved by the coupled solver are shown here. Here, V is the velocity vector of the fluid flow, tau is the viscous stress tensor, E is the total energy per unit mass, K nabla T is the heat flux vector, P is the pressure, T temperature. Note that here in this equation, the source terms such as the body forces have been ignored. To avoid the convergence problems for incompressible flows at low speeds, where it is known that this system of equations becomes stiff, the precondition form of the governing equations is usually solved, as shown here. Gamma here is the preconditioning matrix, which is defined here in this equation, where theta is defined here. Rho T is the derivative of density with respect to temperature at constant pressure. H is the total enthalpy. Cp is the specific heat capacity. Therefore, the preconditioning provides a means to apply the coupled solver to incompressible low speed flows as well. Steady and unsteady coupled solvers. The coupled solver is basically a pseudo-time marching solver that can be used in both the steady and transient simulations. For both the steady and transient simulations, the time marching can be performed using either of the following method: explicit time stepping, implicit time stepping. For steady state simulations, the coupled system of equations is discretized in time, and time stepping is performed until a quasi-steady state solution is obtained. For transient simulations, the explicit time stepping scheme is used when the unsteady time scales are extremely small, such as in the order of the acoustic processes. Other than that, you can use the implicit time stepping for transient simulations. Key parameters of a coupled solver that affect the stability and speed of the solver. CFO, Courant Friedrich Levy. The CFO number is the first parameter which determines the pseudo-time step. The CFO represents the coupled counterpart of the under-relaxation factors, which are used in the pressure-based solvers. If the simulation diverges, the CFO number should be reduced at the expense of reduced overall convergence rate. In some situations, the coupled algorithm combined with the implicit solver will permit very large CFO numbers. Discretization schemes for inviscid fluxes. The schemes that are used to discretize the inviscid fluxes, which are pressure and convective terms in the governing equations as shown here, are another important parameters within the coupled solver. Two popular schemes that are used in CFD solvers such as star CCM plus are shown here. Weiss-Smith preconditioned Rose flux difference splitting scheme, Leo's advection upstream splitting method plus flux vector splitting scheme. They both are developed based on an upwind formulation. The first one is appropriate for subsonic and transonic flows for Mach numbers less than 0.8. However, the second scheme is suitable for supersonic and hypersonic flows for Mach numbers larger than 0.8. continuity convergence accelerator, the coupled solvers have the option called continuity convergence accelerator, which, as its name implies, is a means to accelerate the convergence of the continuity equation. This option is especially helpful in case of the internal flows at very high speeds. When this option is used, we actually add a conditioning step to help satisfy better the continuity equation. Segregated solver versus coupled solver. The general workflow for both the segregated and coupled solvers is shown here. As can be seen here, the main difference between these solvers is that in the segregated solver, the continuity and momentum equations are solved sequentially to obtain the velocity and pressure fields, while in the coupled solver, the governing equations are solved simultaneously to obtain the variables. Thus, the memory requirement for a coupled solver is more than a segregated solver. However, using the coupled solver, less iterations are required to achieve the final solution. Generally, the coupled solver is an excellent choice for high-speed external aerodynamic problems. This is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.